Hi, and welcome back to Codex. Our talks this summer feature graduate students and postdocs who are nominated to speak by their senior colleagues. Today we have Danny Riley, who is a graduate student at Tufts University. Danny will be speaking on the connection between P-frame potentials and T-designs. Take it away, Danny.
Hi, thank you for the introduction and thank you to the organizers for the invitation. A special thank you to Emily, Clayton, and Dustin for viewing an earlier version of this with much grosser graphics. Hopefully I got it cleaned up for this one. I'm going to talk about the connection between P-frame potentials and T-designs. So let's go ahead and start with our P-frame potentials. So we're going to consider a configuration of finitely many points constrained to the unit sphere in RD. So the size n of our configuration is fixed. We're going to choose our dimension d for the ambient space, and then we're going to choose a power p greater than 0. So our p-frame potential is going to be defined as the sum of the pairwise inner products achieved by my configuration x, each raised to the p power. So the goal for the remainder of this talk is going to be what are the minimizing configurations once I give you a value of n, d, and p. And when p equals 2, this was introduced by Benedetto and Ficus in 2003 and shown to be exactly the minimizers of the p-frame potential for p equals 2 are exactly the finite unit norm tight frames. And in general, if we're trying to minimize this thing for values of p other than 2, we'll see that because our points are constrained to be on the unit sphere, the possible inner products that my configuration can take on in modulus are between 0 and 1. So in particular, if I'm trying to minimize this, and n is smaller than my dimension, I can choose any subset of an orthonormal basis, and that's going to obviously be a minimizer because it's going to be equal to 0. So the interesting stuff is going to happen when n is greater than d. And to show you what some of these minimizers look like when we can prove what they are, let's fix d equals 2. So we're talking about the unit circle now in R2. And let's say we have n equals 6 many points on the unit circle. So here I have a range of parameters of p, and I'm displaying what our proven minima look like for each one of those values of p. And you see all the way on the left-hand side, when p is small, the points are tripling up on top of each other. And so I have 6 total points, but it's really 2 unique points on the unit circle, and they lie exactly on the orthonormal basis. And as p gets larger and larger, the points tend to spread out. And in fact, as p goes off to infinity, the thing that we care about is really what is the largest inner product in modulus that I'm computing, if that's what I'm trying to minimize. So it's kind of like an L infinity error as p gets larger and larger and larger for what is the maximum inner product that our points take on. And another thing that you can see with this graphic is that it doesn't actually matter if I multiply any one of my points by -1. So let's say I take one of these 2 points over here, and I actually move this dot over here so they're not doubled up on top of each other. The p-frame potential doesn't see that because I'm taking the modulus of the inner product of that point with all of the other points and I'm raising it to the p-th power. So you can equivalently think about this as trying to pack lines optimally in dimension D. So that's one of the subtleties there. And the goal for the remainder of the talk is to try to describe what the techniques are used for showing that we have our minima and try to fill in the gaps for where it doesn't quite work out. So what I have here is when I fix dimension d equals 2, here's a graph of our parameters n and p, where n is the number of points, p is the power of my p-frame potential. And I've filled in whenever we have a proof for what the minimizing configuration is. And you can see that there's gaps and that the gaps get larger and larger as n gets larger. But what you can also see is because it's colored by proof technique that most of the proofs rely on linear programming techniques. So I'm going to cover what exactly those are. I'm going to show the necessity of them and describe what some of the shortcomings are, like why can't we use that to fill in the gaps in the middle? And I'll suggest a weaker notion of T designs to begin to fill in those sort of gaps. Okay, so the title of the talk is P-frame potentials to T designs. So how do I go from P to T? Well, I'm going to be a little cheeky here. We're going to say the P-frame potential minimizer is quadrature points. Okay, so we're going to have to talk about interpolating polynomials. Okay, what comes next? PQR. So they're either really good strength or really bad quality, and it depends on this condition here, which we'll see later. For the spherical harmonics, so in other words, we want a T design, but not a T plus one design. So that's kind of the roadmap for the rest of the talk, and I want to break down what each one of these are, how we go from P all the way down to T. Okay, so there's the P-frame potential again. I just rewrote it in case you forgot. We can think about the P-frame potential in several different ways, and here are two. On the left-hand side, I'm thinking of my potential F as a function of points that lie on the unit sphere. So X and Y are points on the sphere. And what is my P-frame potential? I'm just evaluating that raised to the P power, and I'm summing that up over all the points in my configuration. But on the right-hand side, I can think about my P-frame potential instead as a function on the interval -1 to 1, because those are the possible inner products that can be taken on by points in the unit sphere. And what my P-frame potential is I'm summing over that potential evaluated at the inner products that my configuration X achieves. And okay, how are these two different, but also how are they related? Well, on the left-hand side, because these are functions on the sphere, at least for a fixed value of y, is a continuous function, so it has a spherical harmonics expansion. Now, if you've not heard this phrase before, all this is just a generalization of the Fourier series, but for dimension d, possibly greater than 2. But it acts the same way. You're decomposing your continuous function into polynomials that are on the unit sphere, but now we might be in a higher dimension. And on the right-hand side, well, this is a continuous function on the interval -1 to 1. I can expand this in terms of any basis that I want. Specifically for this, we're going to choose the Gegenbauer polynomials. And why are we going to choose those in particular? Well, because they're related to the spherical harmonics by the so-called addition formula, which I've written down here. Now, something to note here is that for higher dimensions, when d is greater than 2, there might be several spherical harmonics of degree n. Hence, that's why we're summing over up to this dimension. This dimension hn is depends on what my dimension little d is. But the point is that inner products for my Gegenbauer polynomials can be seen by spherical harmonics as functions on the unit sphere. So I'm going to rewrite this relationship that we have down here to just try to describe where this comes from. Like, why are we choosing Gegenbauer polynomials in particular? Okay, so that's just the equation that I have up at the top. And if these y and j's are spherical harmonics, they're an orthonormal basis for continuous functions on the unit sphere. What are they orthonormal with respect to? They're orthonormal with respect to the uniform measure. So what I've drawn on the left-hand side here is, at least for dimension d equals 2, this is the unit sphere or the unit circle because we're d equals 2. If I fix a direction x, what I want to do is try to project the uniform measure of the circle to some measure on the interval -1 to 1. It's going to depend on my dimension, but for here in d equals 2, I fix a value u0, and I'm going to look at the points y such that their inner product with x is equal to that constant. And I'm going to take a little epsilon width of the uniform measure on the sphere and project that down onto the line in the direction of x. And so on the right-hand side, what I have is how much of the uniform measure, in other words, how much of the length of that circle for that little epsilon width is when projected down onto that line. So the Gegenbauer polynomials, these CNs that I have up here, are orthonormal polynomials. What are they orthonormal with respect to? Well, they're orthonormal with respect to this weight. In general, the power on 1 minus u squared is going to be different. It's going to depend on our dimension. But for d equals 2, this is what it's going to look like here. Okay, so we know we're not just choosing arbitrary polynomials. There's a reason why these two are connected. Now I'm going to try to utilize this to leverage this and to show what our minimizing p-frame potentials are going to look like. So suppose I have the Gegenbauer coefficients of my p-frame potential where I'm now thinking of the p-frame potential as a function on the interval -1 to 1? Well, just by expanding a function in terms of an orthonormal sequence of polynomials, I know there's some coefficients f hat that satisfy this relationship right here. They're connected to the p-frame potential because if I throw in a sum over the pairs of inner products achieved by my configuration, okay, I do that on the left-hand side, I do that on the right-hand side, I apply the addition formula for spherical harmonics that we saw a couple slides ago. I need to worry about convergence of series. I need to make some simplifications. So I'm just going to throw this all up there and say, this is kind of gross. It's a lot. If anything, I've taken a step backwards because up here on the top left, I have a finite sum. And on the bottom right, I have this f hat over all parameters n greater than or equal to 0. I have an infinite sum. So, okay, this kind of seems bad. We're going to need to make some simplifications in order to actually utilize this to prove what our minimizing configurations look like. So I'm just going to rewrite the conclusion here. We have our p-frame potential equals this thing right here. And here's where our linear programming bounds come into play. How do we simplify this equation on the right-hand side? Well, on the one hand, we want to come up with a uniform lower bound for our p-frame potentials. So we're going to replace our f hats with h hats, where h is a function that's less than or equal to my p-frame potential. And I'm also going to choose these coefficients to be positive, which we'll see in a slide why that's important. But if I have this lower bound, then okay, I just now expanding h hat instead of f hat. I'm going to choose h hat to be 0 for only, or excuse me, I'm going to choose it to be non-zero for only finitely many values of n. And let's just say that that's equal to t. So I've converted that infinite sum into a finite sum. And then, well, let's look at the other term over here. Now I'm going to choose my configuration x such that this thing is going to be equal to 0. Well, why am I doing that? If I'm trying to show what is a lower bound on the p-frame potential, what is the smallest that this thing can be right here? Well, if all of the h hat are non-negative, I need, whenever h hat is positive, for this thing to be as small as possible. And it's something squared, so the smallest of this could be 0. So what I want is for all j, I want the sum of the spherical harmonics of degree n and phase j to be equal to 0. When do I want that to happen? That's whenever h hat is non-zero. And if it's 0 for n greater than t, I need this condition for n between 1 and t. If all of that is true, then this sum actually becomes very easy because it's a bunch of 0 times something else or something else times 0. This is just the constant h0 as long as all of these assumptions are met. So the big question is, can all of these inequalities simultaneously be sharp? In other words, if I get that there is this lower bound h hat 0, and I know that there's a configuration x such that this third bullet point is true, I know that there's an h such that this first and second bullet point are true, then I've proven what the uniform lower bound on the p-frame potential is. And further, I've shown that there is a configuration x that actually equals this thing right here. So that's how I show global optimality. But the kind of problem with this is that it's a lot to ask. So specifically this third bullet point right here, I'm just going to rewrite. If we want to choose our x such that our this condition holds for all n between 1 and t, well, if these spherical harmonics are a basis for our continuous functions on the unit sphere, then this is equivalent to demanding that x exactly integrates our spherical harmonics for degree 1 through t. And because they're an orthonormal basis with respect to the uniform measure for continuous functions on the unit sphere, that's the same as saying x exactly integrates polynomials up to degree t. In other words, it's quadrature for a certain strength, and that strength is whatever my value of t is. And so that's what our definition of a t design is. It's just any configuration x such that that condition holds. In other words, it exactly integrates any polynomial of degree between 0 and t on the unit sphere. Okay, so that's how we show that all of those linear programming techniques work and prove what the minima are, is because we can find an H that has those properties, an X that is a T design of appropriate strength. But in general, this might be too much to ask of our configuration X. It depends on our parameters, P, N, and D. But for certain combinations, it's just simply not going to work. So we need to kind of relax this a little bit. And that's what I want to talk about for the remainder of this talk. So we're going to focus on the case when d equals 2. And because I'm dealing with R2, I'm just going to identify that with the complex plane, just because it's going to make notation a little bit easier for subsequent slides. So I've rewritten that sort of nasty condition I had before we made all of the assumptions that come with the linear programming bounds. So we no longer want to ask so much of our configuration X. So let's just try to find like what properties we can deduce from our p-frame potentials here. And I'm going to start with the Gegenbauer coefficients of f hat. So rather than replacing this with an easier function, we're going to go straight into looking at what it is for our actual p-frame potentials. And so my contribution is I can show that these coefficients are 0 whenever n is odd, and hopefully that makes sense because our absolute value u to the p is an even function. So it's going to be coefficients are 0 for the odd polynomial expansion. All the coefficients are positive for our even n up to something which is essentially just p. And then it alternates in sign for all subsequent even n and decays like order n to the -4. It's some nasty formula, but these are the sort of important properties of our p-frame potential. So with that in mind, whenever f hat is positive, if I want to show that something is a minimizer, I want whatever I'm multiplying that f hat by to be very small. And when f hat is negative, I want whatever I'm multiplying that by to be as large as possible. And so what we're going to look at now is what are the things that I'm multiplying f hat by? And can I control them to try to show global optimality for a configuration? Okay, so let's focus in on the other term. Now, things simplify because we're in dimension d equals 2. So the dimension of the spherical harmonics is there's only one j that satisfies this. It's the Fourier expansion. In other words, I'm just taking the nth power of the points in my configuration x, and I'm summing them up. I'm going to go ahead and call this the nth power sum for my configuration x. And what we see is, well, it's relatively easy to compute once I have a configuration x, what my nth power sum is. I have an explicit formula for it. But what if I want to go the other way around? What if I instead want to show what is the smallest that that series can be when I multiply it by f hat? In other words, suppose I don't know what my configuration x is, but I only know what its power sums are. What if I start with that? Can I choose these Pn such that I know they must come from a configuration of unit norm or unimodular points, such that this infinite sum is as small as it possibly can be? For example, if I choose Pn equal to 0 for all values of n, well, we know the only configuration that can do that is just the 0 vector over and over and over again. Okay, so that doesn't come from a set of unimodular points. So what are the sort of properties of these Pn's? Let's try to examine that. So if I start with a configuration X and I want to detect if if the points are unimodular, something I can do is write out a polynomial in terms of my variable z for my fixed values of xl, and I get that it's just some expansion of powers of z right here. So the thing is that Newton's identities tell us that if I don't start with these xl's, but instead start with the power sums, I can write out these coefficients as a polynomial in terms of the power sums p1 through pn minus j. And then once I have that, I can try to detect if the roots of this polynomial are unimodular, because it's important that we assume that each one of our vectors was unit norm. Now, famously, root finding is, like a very hard problem. And, for n greater than or equal to 5, that might not be the best way to sort of go about this. But we can try to deduce the properties of what these coefficients must look like so that we can try to see what our Pn's are going to look like. So if this polynomial came from a set of points that are unimodular, then there exists some common rotation of all of the points in our configuration such that our coefficients have this conjugate symmetry to them. So this is a sufficient, or excuse me, this is necessary, unfortunately not sufficient to conclude that our roots are unimodular, but what it does give us is a reduction in the number of variables that we have to worry about here. So let's say I give you a big N, and I want to talk about what are the possible values of the power sums P1 all the way up to Pn. Like how would I know that a unit norm configuration could possibly produce that? Well, if I get this conjugate symmetry right here, then I would know C0 all the way up to, well, Cn over 2, and then all the subsequent ones would be determined by just the complex conjugate of the earlier ones. In other words, if I know and I stipulate that my configuration X is unit norm, I only need n over 2 many power sums to determine what my configuration X is going to be. It doesn't necessarily mean that it's unit norm because this isn't a sufficient condition, but it at least gets us closer to that. And so now the name of the game becomes, I know what f hat is. I know it's positive up to some bound, and then it starts alternating. Can I choose these pn's such that they're large when this is negative and small otherwise? So that's the sort of reframing that I want to give for how we know that our minimizers are global minimizers and to begin to fill in the gaps. So let's apply this thinking to the results that have already been shown. These are shown using linear programming bounds, but I want to recast it in a sort of different light. So let's focus in on this middle case, for example. P is between 2 and 4. Since I know what P is, I know what D is, I know what N is, I can compute what these coefficients are on the Gegenbauer expansion, and I see that it's positive for N equals to 0, 2, and 4, and then the N equals 6 term is negative. So the name of the game is now, given that I want P2 and P4 to be as small as possible. In this case, they're equal to 0, but maybe I didn't know that a configuration could achieve that. What is the maximum across all 6-point configurations of this sixth power sum? And that's going to be given by this doubled up configuration right here. And the same thing applies for P between 0 and 2, but that just changes how many positive terms I have, and same with other values of P. So the fact that the minima of the P frame potential are equivalent to the minimum of these right here give us a sort of insight to what the P frame potential is actually minimizing and to determine how we might go about doing this in the cases where our linear programming techniques are asking too much of our configurations. So just to summarize everything that I said there, you could say that the P frame potential is quadrature points of really good strength or really bad for spherical harmonics. So we want a T design, but not a T plus 1 design for a well-chosen value of T. So I'll leave it there. Thanks for your attention.
All right, let's smash those reaction buttons.